So the format for my talk is that I will talk briefly about University of Glasgow. Then I'll talk about why we need 6G. Then I'll be touching a very hot and interesting topic which Dr. Qasim, Dr. Zubair and their team is working as well. And then I will be talking about some of the opportunities um, we have in University of Glasgow for the students and staff. And end of the talk is around 10 minutes about IEEE Antenna and Propagation Society, which has so many opportunities for students and staff both. So if you want to follow me, here is my LinkedIn QR code. You can follow. There are so many opportunities I share on LinkedIn as well. So you can scan it. And I graduated from UET. I'm originally from Murray, like Qasim was saying, he is from underprivileged city. So me too. So I know the importance of these things which change your life and future. So I'm so glad to be here speaking to people who are roughly similar to me in terms of background. So, okay. So if you don't know where University of Glasgow is, it is somewhere in the north of UK. It's one of the fourth oldest university in English speaking world after Cambridge, Oxford and St Andrews, established in 1451. And it is home to various Nobel laureates, including John Logie Baird, who made television, James Watt, we all have studied in our school, colleges, Lord Kelvin, unit for temperature. And Lord Kelvin was a person who basically laid the first optical fiber between North Atlantic and UK. William Rankine, 2021 Nobel laureate for chemistry, was from University of Glasgow. First X-ray developed in University of Glasgow as well. In conclusion, University of Glasgow has a deep history of innovation. Okay, so I got it. So I have to align it on that side. So in University of Glasgow, I am basically director for communication sensing and imaging hub, which has more than 140 researchers from around the globe, and out of 140 researchers, 30 are from Pakistan as well. And also we have like Qasim was mentioning about commercialization. So we go from concept to commercialization. We strongly believe on C2C. And we have three spin-offs coming from our hub as well. I'm founder for two of them, RFIoT and Diabetes Companion. So let's get to the work. So before talking about these reconfigurable intelligent services, I want to make a story that why we need, or I want to make a case why we need 6G. So I'm sure none of you were born when mobile communication came in 1980. Only Dr. Qasim must be born, no one else. So, so even none of us were born. So let's put it this way. So 1G came in 1980s, and every 10 years we have a new generation of mobile communication coming. Each generation was better than previous generation. But the real change came when 5G came to market. So up to 4G, we were talking about only mobile communication, mobile to mobile connectivity. But when 5G came, we started talking about an ecosystem connecting other devices as well in addition to mobile. And then 6G came. It's already, there are discussions going on. But there's a big issue with 5G. So everything is driven by money, unfortunately, return on investment. So I was in Mobile World Congress last year. It's the world largest mobile expo, where there are around 200,000 people coming from all around the globe, mostly companies. And for the first time since mobile's inception, there was low return on investment. Companies were not happy that they're not getting return on investment and they are firing people because there is so much cost to putting 5G, but there is no money coming. Because we know that whatever you can do with 5G, mostly I'll talk about myself. I can use WhatsApp, I can watch movies, YouTube on 4G as well. So why I need 5G? So the problem was that 5G was being developed, but there are no use cases or not many use cases which needs 5G. So the question comes that do we really need 6G? That uh, I'm sure you have seen in news that South Korea has basically withdrawn 5G. So they have deployed 5G and no have they have withdrawn because there is no return on investment. But as time goes on, the need for mobile data is increasing. Like we have around 67% of the global population. No, I'm making the case for 60. So listen carefully. So now we have around 67% of the global population using mobile phone, mobile data, and normal people spend 7 to 8 hours a day. People like Dr. Qasim spend 12 to 13 hours a day on using internet. So, so uh, this shows that the need for internet in our life is increasing day by day. We can live without food, but it's very difficult to live without mobile phone and internet. And one of the challenge with up to 5G was basically what we do. We set KPIs. You know, whenever we want to make some system, what we do, we set KPIs that this is what we want, and then we start making a network. And this was the reason for failure of 5G, that KPIs were being set up, system was being made, and then there are no use cases which needs 5G. So there was no return on investment coming. So what we thought that let's not talk about KPIs for 6G. Let's go other way around. First of all, find some use cases which need 6G. Then you start making 6G network. So we came up with a very interesting use case called Internet of Senses. So can anybody tell me how many senses we humans have? 5. But some genius people like Dr. Tokir have 6 as well. But normal people have 5 senses. So up to now we can transport 2.5 senses from point A to point B. Hearing by using an audio call, vision by using a video call. You have seen robotics, touch by using haptic, but we are unable to transport smell and taste. And I'm sure you all have seen holographic communication as well, a holograph which is being teleported from point A to point B. Imagine that I teleport all 5 senses from point A to point B with a holograph, means a holograph with all the 5 senses. It means I'm teleporting a whole human with all the senses. So you are sitting in Pakistan, but your holograph with all senses can be in UK because you can sense all the 5 senses, or you can teleport all the 5 senses. This looks simple, but this is very challenging. If you want to teleport all 5 senses from point A to point B, you need ultra low reliability, ultra high throughput, and ultra high bandwidth. For example, 1 inch square meter of your palm needs around 1 gigabits per second of data. Imagine if I want to teleport all the hand with different textures. So it's need humongous amount of data. So you are getting it. I'm making a case that we need ultra low reliability, ultra high throughput, which is not possible with 5G. So we need something new, which is 6G. So there is at least one use case I just showed you, which cannot be catered by 5G. And there are so many discussions going around what will be the elements of 6G. But one critical element would be ubiquitous AI, that it will be an autonomous AI enabled network. And it will enable various other use cases in addition to what I mentioned, including hyperloop, bullet trains, uh, remote surgeries, and so on. No, so I convinced you all that we need 6G. No, I'll talk about the enabling research which we are doing in our hub for 6G. There are so many things we are doing, but in the interest of time, I'll be talking mostly about intelligent reflective surfaces. But before going into detail, I'll briefly discuss about antennas. So antennas are ears and eyes of wireless communication system. If we do not have antennas, there will be no wireless communication system. And for 6G, antennas are more critical because we are talking about terahertz band for 6G. The challenge there is that the traditional materials like copper, aluminium, which we use, will not work. So we are looking at some new 2D materials to make those antennas, including graphene, maxine, perovskite, because these 2D materials have surface plasmon phenomena at terahertz, which help us to overcome the challenges posed by terahertz. So in our hub, we have made various world first terahertz antennas by using combination of materials from graphene to titanium. You can see those and you can see their size as well, so tiny. And the reason we are able to do these things is that we have everything under one roof, from modeling to fabrication, where we have James Watt Nano Fabrication Center, and we have world-class measurement capabilities going from 10 megahertz up to 1.1 terahertz, which help us to do these challenging fabrication. So let us come to the topic, which is intelligent reflective surfaces. So I know some of you are working on this, but for some of those who do not understand this, let me explain this to you. So this is Hunterian Museum in University of Glasgow. Imagine we want to provide a coverage to the user. She's using a mobile phone sitting there. So whatever signals are reaching to her, there is no direct path. We have reflection, diffraction, scattering. So ultimately, the signal which are reaching to her will add up constructively or destructively. Ultimately, quality of service will reduce. But imagine if I put something on a wall, what it will do, it will focus the beam on the user. Ultimately, the quality of service will improve. And let me tell you, this is nothing new. This has been done by Muslim scientists hundreds of years ago. When we do not have electricity, how we used to control the light? By using mirrors, right? So this is a very similar concept. Here we are controlling electromagnetic waves by using electromagnetic mirrors. So these are called reflective intelligent surfaces, meta surfaces, IRS, whatever you say them. And they have applications in all domain of life, ranging from communication to sensing, and I'll be talking about healthcare sensing later on as well. So in next 10 minutes, I will be talking about some of the work we are doing from last 7-8 years in this interesting topic. And I'll be talking about the designs, then the actual trials in indoor and world first outdoor trials, then the risk for healthcare sensing, and I'll not be touching remaining topics because of less time. So we have developed various large-scale, world-first RIS test beds with various specifications ranging from 1 bit to 3 bit, single polarized to dual polarized, going from low frequency of sub 6 gigahertz, which is 3.75 frequency for 5G, going up to millimeter wave and terahertz as well. And we used various kind of switching functionalities, which was pin diodes, vector diodes, and ink as well. So the first test bed was basically a 1-bit RIS. When I say 1-bit, it means it can change the phase of incoming signal by 180 degrees, 0 or 180 degrees. So how we design RIS is you make a meta cell, which is on the right hand side. We have a patch. We design that and then we replicate that to make a tile. And the reason for making tile is that it gives you flexibility, that once you have designed one tile, you can replicate it to make any kind of structure you want based on the requirement. So our first test bed had 16 tiles, in total 4096 unit cells with 4096 pin diodes, and the total dimension for this structure was 1 cross 1.4 meter, and mentioned it was working at 5G frequencies, which was 3.75 gigahertz. And the switching elements we were using were pin diodes. Remember the power consumption, it was 15 watt, I'll ask you later. And the switching speed was 20 milliseconds. Then this test bed, because we were able to control each unit cell. If you remember, there was one pin diode in each unit cell. So it means you can control each unit cell. Ultimately, you can achieve near field performance and far field performance both as well. The second test bed was 3-bit RIS. When I say 3-bit, it means you can change the phase of incoming signal by 2 raised to the power 3, in total 8 states. And second thing we did was that instead of making unit cell control, we made a column control structure, because whenever you design a system, you need to look at performance and cost both. So this test bed had 2300 unit cells. The total dimensions were 1 cross 0.7 meter. In total, we had 6 tiles. And you can see the control circuitry at the back where we were using Raspberry Pis and FPGA. And the purpose was to put the configuration to turn on or turn off certain unit cells to get the desired performance. Now we made the RIS. We want to test whether it works or not, right? So the first thing we did is we took an ideal environment, which is anechoic chamber. We took this RIS to the anechoic chamber to see if we have similar phase and amplitude performance or not. You can see in the bottom figure, we have 8 different states of phase. There were some kind of anomalies in the amplitude, and the reason was our 3 of the pin diodes were broken, which we found out later on, but we sorted that out. No, it worked in an ideal environment. The first question is whether it gives the coverage enhancement, which is the main purpose of RIS, in an actual environment or not. So what we did indoor trials. So we designed special experiments. I will not go in details, but it took us a month. So you can see we selected various scenarios, including corridor, lobby area, multi-floor scenario, where we were using horn antennas as a transmitter and horn antenna as a receiver. If you look at the corridor junction scenario, and RIS was somewhere in the middle. Remember this, that we were using directional antennas. So what is more important is the results. So ultimately, we prove that we can get a coverage enhancement of around 20 dB on average by using RIS and in indoor scenario. So I was delivering a keynote, so I'll come back to this point later on. So can somebody tell me that what was the power consumption in previous case for the big RIS? 15 watt, well done. So we were super excited. We were working with world largest telecom operator, British Telecom. We went to them, we said, oh, look, we did a breakthrough. As a researcher, we always get excited. Look, we did a breakthrough. We have a 20 dB coverage enhancement. And they asked us, what is the power consumption? We said 15 watt. They said, are you crazy? 15 watt for this structure, it does not make sense to us. We had to go back. We got demotivated. We started thinking again. The major component which was consuming power was those switching elements, pin diodes. So we came up with a new idea, which was, of course, very basic, like Dr. Toshi was mentioning in the morning, that there are very simple problems which we can solve to change the world. So we went back to the basics, and we remember that we studied in our undergrad that varactor diodes works in reverse bias. So instead of using pin diodes, we started using varactor diodes because they work in reverse bias. There is no current. So ultimately power consumption was reduced from 15 watt to few milliwatt. So our problem was solved, that we have reduced the power. And second benefit we got was that in the previous design, once you have fabricated the design, you cannot change the center frequency. But in varactor diode, you can change the voltage to change capacitance. So ultimately, you can change the center frequency as well. And the third thing, which British Telecom told us, was that we do not know the polarization of incoming wave. So we want a dual polarized race. That was not a problem. So we made a new race, which was 1 bit varactor based dual polarized race. It had, you can see, 4 tiles, and power consumption was reduced to few milliwatts. We were able to change the center frequency as well, and we were able to do beam steering as well. So this was the simulated results, where we were able to do beam steering from 0 to 180 degree. But then we went to University of Southern California to use their channel sounder to see if we can do beam steering in reality as well. And there was a great agreement between simulation and measurement. You can see the red one is measurement and blue one is simulation, which shows that we can do with our race beam steering as well. Then one of the key elements for 6G would be that up to 5G, I told you that up to 4G, you can do only mobile communication. In 5G, you are able to connect an ecosystem. In 6G, one key benefit would be that you can do joint sensing and communication. That up to 5G, using mobile communication, you can do communication only. But with 6G, we'll be able to use same spectrum for sensing and same spectrum for communication as well. I'll show you a demo later on for that as well. So what we were doing was that we were using a radar at X band to do communication and sensing. But for non-line of sight scenario, we need some support, which was RIS. So we designed a RIS in X band. Mechanism was very similar. We designed a meta cell, where we were able to get gain of more than 20 dBi at bore side, and we were able to steer the beam from 0 to plus minus 14 degree in this case. It's okay. It's okay. So I can speak without slides as well. That's fine. So we designed this race. You can see this is the race. And if someone remember, in the previous race, our switching speed was 20 milliseconds. So what we did here, we have improved our control circuitry. You can see it is at the front side, and we had did some kind of optimization. Ultimately, the switching speed was reduced to 0.5 microsecond. You can see that over the years, we have improved our design in all aspects. Then we are, if, okay, it's not working. You can sit there and you can move the slides with the arrow. So then we designed millimeter wave race as well in N257 band, where we were able to get an angular stability of 30 degree. Last but not least, one of the biggest benefit of using these race surfaces is that can we paste it on a window so that we can get enhancement in probably especially in basements or indoor scenario. So we designed that race. It's not moving. We designed that race by using silver nanowires as well. So ultimately, we have basically progressed slowly towards taking this thing to commercialization. You can see our design is improving day by day. Now we are basically providing this race to various industries and universities to do demonstrations, testing, prototyping. So remember the word I said, concept to commercialization. So over the years, we have taken this to commercialization scenario. So this was the race for communication that we have demonstrated that we can use this for enhancing coverage enhancement. But one of the unique work we did is that how we can use it for sensing. So let me tell you the story for this first. Okay, so this is race for sensing. So, you know, as I mentioned that we can live without food, but we cannot live without our mobile phone. So with the passage of time, our life is changing. So we are moving from doctor-centric healthcare to patient-centric healthcare. What I meant here by doctor-centric, we go to doctor, we tell them our symptoms, and they prescribe something. And patient-centric is I have smartwatch, I have mobile phone, can I monitor my health myself? So the idea is that in future we are going to have a smart home which will have various kind of sensors in it, which includes point of care devices, which include wearable, implantable sensor, environmental sensors, and these all sensors will work together to collect a multimodal information, securely send to cloud where we will apply AI to that to do proactive healthcare detection. And to remain within topic, uh, I'll be talking about contactless sensing. So what is contactless sensing? We know that we have ambient radio frequency signals around us, mobile signals, Wi-Fi signals. Can we use those signals to monitor someone's health without using any wearable devices or implantable devices? Because what happens is that whenever signal passes through the channel, there are certain kind of perturbations occurring channel state information in terms of amplitude and phase. We look at those changes to monitor someone's health. So this work was being done 10 years ago in MIT lab, but the challenge was threefold. Number one, with these ambient radio frequency signals, we cannot control them, right? So ultimately, resolution was low. Number two, if we have multiple subjects in a room like this, I can know the heart rate or breathing rate of someone, but I cannot tell it belongs to whom. Number three, if one of you will start moving, I cannot localize the target. So these were the challenges with contactless sensing, in addition to one major challenge, which was that the subject needs to be in line of sight between transmitter and receiver for contactless sensing. And I'm sure you got it, how we solved it. So we use these reconfigurable intelligent surfaces because you can control the beam, you can steer the beam. Ultimately, you can enhance the contactless sensing paradigm. Okay, so what we did that, yeah, so what we did was we published in Nature that how we can monitor people in a non-line of sight scenario contactlessly. So what we did, we designed a special experiment in an indoor scenario where, go to previous slide, where we had, as you can see, transmitter at one corner, receiver at the other corner, cannot see each other, and user was performing some activities in activity zone. So if you move to next slide, we did a thorough campaign of experiment, but what is of interest is the results. If you go to next slide. So when there was no risk, we were unable to detect or classify any activity. But as soon as we turned on the risk, ultimately, we were able to detect any kind of activity with an accuracy of 100%. So this work was done almost 3-4 years ago. We have went so far in this. And then we use this, if you move to next slide, please. We use this in a very interesting problem, which was hearing aid devices. So I'm sure we have many of our relatives around who have hearing impairment. If you speak to them, they hate to wear hearing aid device because they have a noise which is called cocktail effect. Cocktail effect is that I have made my hearing aid device with a certain noise threshold. So it will work here because it's a quiet environment. If I go to cafeteria, the noise threshold is different. So that cocktail effect will enhance. So ultimately, it's a noise for the user. They do not like to wear it. So we thought that can we make these hearing aid devices intelligent, inspired by brain? For example, when I'm currently speaking to you, your brain is interpreting what I'm saying not based on my audio only. It is looking at my body language, my facial expressions, slides, pictures, combining them all and then interpreting it to a useful information. So we use the same concept that can we make hearing aid devices intelligent and smart so that they take all the multimodal information, including audio, facial expression, lip movement, body language, combine that all so that it adjusts the noise threshold because usually a person goes to certain location in their normal routine, right? Like when to see friends, when to cafeteria, when to mosque. So you know that environment. So ultimately you can predict the noise threshold based on the daily routine of the user. So inspired by that, we started making our hearing aid device. So one of the challenge came was that we wanted to do lip movement. So we were using a Google glasses which had a camera which can do the lip movement. But when pandemic came, everybody was wearing a mask. The camera technology failed. And we know that RF waves can penetrate. See, very simple idea, nothing rocket science. RF waves can penetrate through the mask, through the clothing. We were able to do lip movement. And we published this work in Nature Communication. And then this was again a 4 years old work where now we have progressed so much that we have a system on chip where we have audio, lip movement sentences embedding into the hearing aid device, which is work in progress. And then we were using some kind of meta surfaces on the mask, which is another work where we were focusing the beam on the user. So if you move to next slide, yeah, next slide. So then we were using, as I told you that the mechanism for contactless sensing is if you look at the bottom right corner, that user needs to be in between transmitter and receiver. So what we demonstrated is on the left hand side that you can do the vital signs, which is breathing and heart rate for user in non-line of sight scenario as well by using reconfigurable intelligent surfaces because you can focus the beam. And we were doing benchmarking with off-the-shelf sensors, which were bipolar sensor for heart rate and go vernier belt for breathing rate. And we demonstrated that you can detect the heart rate and breathing rate in non-line of sight scenario with an error of 1%. We have a spin-off on this as well, patents as well. And then I'm showing you some of the examples in healthcare. So if you remember during pandemic, there was in the news that people were saying that 5G is the reason for COVID. So UK government came to us and said to us, give us some justification what we say to the people because they were burning the base stations and masts in UK. So as a scientist, we need some scientific backing. So what we demonstrated that if we use race, so what we can do that we can reduce the uplink power. Ultimately, one of the parameters which causes impact on human is called specific absorption rate. So if transmit power has been reduced, specific absorption ultimately reduces, which proves that if you use RIS, you can make 5G or 6G more secure. Then we use this for brain-computer interface, that how we can use these RIS surfaces for transmitting the textual information through BCI from one operator to another. Next, please. And last but not least is joint sensing and communication. I think I bored you enough, so this is the last thing, which is I told you one of the key feature for 6G is using the same spectrum for doing communication and sensing both. And the benefits are so many, including spectrum efficiency, cost saving, security, and privacy. And I think I'll stop at this demo. So what this demo, if you click, so what this demo is showing is world first joint sensing and communication demonstration. So in number 3 on right hand side, we are using the spectrogram, which shows basically which has embedded breathing rate and heart rate for the user. And number 4 is the read range. So we have our in-home developed radar. So as users are moving, you can see in figure 4 that read range is moving, which is basically communication happening in real time. And number 3 is sensing, which is heart rate and breathing rate embedded in spectrogram, which we have already de-embedded. I didn't show here. But the key here is that you can see that as users are moving, communication is happening at 4, which is showing how they are moving, and sensing is happening in 3. So I think I will, yeah, next slide, please. So I was thinking what to put in summary. The key message is future is here, and we all need to work together to make this happen. So thank you very much for listening. The first part.